Hi everybody, my name is Sophia Rupp. I'm a master's student at the University of Delaware working with Professor Yvonne Tatar, and I'm also an engineer at a company called CFRP. My research project at the University of Delaware is focused on the durability of carbon fiber splay anchors in bond-critical externally bonded CFRP under hygrothermal conditioning. There's a lot of existing research so far with respect to the effects of environmental exposure to CFRP concrete strengthened members. And from the research that's been completed so far, it's been concluded that moisture is the most detrimental to strengthened members. In addition to this, it's also been concluded that the deterioration that's reported isn't necessarily deterioration to fiber-controlled properties, but rather epoxy-controlled properties. When epoxy is exposed to moisture, it loses its stiffness and it also softens. And because of this, we see a loss of adhesion and mechanical interlock between the concrete substrate and the epoxy, which leads to debonding. In addition to this, moisture exposure to epoxy also results in a decrease in the fiber matrix interface, as well as a decrease in interlaminar shear strength. Due to the adhesive failure leading to debonding, there's a need to include some form of anchorage, such as carbon fiber splay anchors, to mitigate this detachment of the FRP after debonding initiates. If you're not familiar with carbon fiber splay anchors, it consists of two main components, the first being the anchor dowel, which is what is embedded into the concrete, and the second component being the anchor splay, which is what is fanned out over the CFRP and does the anchoring. So given that we know we need to include some form of anchorage to mitigate this debonding, such as carbon fiber splay anchors, there's a knowledge gap in regards to the effects of moisture exposure on the durability of the installed carbon fiber splay anchors. With this being said, the objectives of my research, or at least one of them to start off with, is to quantify hygrothermal conditioning on the externally bonded anchored CFRP system. Hygrothermal conditioning is just a fancy word for the combination of moisture and heat. And then the second objective of my research is to evaluate the effects of the selected accelerated conditioning protocol on the constituent materials used for beam strengthening. The accelerated conditioning protocol that was selected for this study was in accordance with ACI 440.9R, in which it suggested to immerse the strengthened beams in water at a constant temperature of 50 degrees Celsius for a duration of 3,000 hours. The accelerated conditioning protocol group, will refer to that as the ACP group, and then in addition to that, there needs to be an unconditioned control group that's held in standard laboratory conditions, and we'll refer to that as the SLC group. The SLC group had concrete compressive strength of 7,200 psi, whereas the ACP group had compressive strength of 9,000 psi. The reason being that after conditioning the concrete cylinders, it was found that the concrete compressive strength increased. The concrete mix consisted of 40% cement, 60% slag replacement, and in addition to that, 5.5% of air entrainment was also included. We included slag to minimize substrate degradation, and we included air entrainment to promote better adhesive concrete mechanical interlocking. The reason being is we didn't want to observe any effects of the adhesive layer deteriorating, but rather solely focus on the durability of the carbon fiber splay anchors. As for the material used for strengthening, a unidirectional carbon fiber was used, and a low viscosity epoxy was used to prime this concrete substrate, as well as saturate the fibers. In addition to that, putty was also used as a concrete substrate primer, in which it's used to fill any voids in the concrete, and that's the low viscosity epoxy mixed with 5.4% by weight of silica fume. The strengthened beams were small scale concrete beams. They were 6 inches wide by 6 inches high and had a span length from support to support of 18 inches. And those beams were tested in 3-point bending in order to assess the durability of the carbon fiber splay anchors. Epoxy and putty were both tested using DSC to classify their glass transition temperature. And CFRP coupons and epoxy dog bones were tested in tension for their mechanical properties. Both the concrete beams and the constituent materials, as mentioned, were split into two main groups, the first being the unconditioned group, which is the SLC group, and the second being the conditioned group, which is the ACP group. Beams also consisted of bonded beams and unbonded beams. Bonded beams consisted of direct bond between the CFRP and the concrete, whereas the unbonded beams consisted of a bond breaker in between the CFRP and concrete. This was included in order to mimic complete deterioration of the adhesive layer to assess the performance of the anchors under a case as such. Anchor diameters were also varied in this study between 1/4 inch, 3/8 inch, and 1/2 inch. What I have next to these anchor diameters is the AMR, which AMR stands for anchor material ratio, which is the ratio of the cross-sectional area of the carbon fiber splay anchor to the area of the flexural strip in which it's anchoring. The reason we selected the anchor diameters that we have here was in order to, it's because existing research has shown that when an AMR of 2 or greater is used, you can obtain strip fracture. So we wanted to observe AMRs that were less than 2 as well as greater than 2. There were a few steps required to prepare the concrete beams for strengthening, which included first drilling anchor holes into the beams, and after that was followed by chamfering the anchor holes to reduce stress concentrations at the joint region between the anchor dowel and the anchor splay. Shear wraps were also wrapped around the sides of the beams to mitigate shear failure, so because of that, the corners of the beams also had to be chamfered. A notch was introduced to the tensile face at the center line to control the location of the initiation of the concrete cracking. And then lastly, the concrete surface was sandblasted for better CFRP concrete bond. As for the strengthening of the beams, the concrete surface was prepared with a coat of epoxy as well as a coat of putty. However, that's for the bonded group. In the case of an unbonded beam, those 2 coats or primers were skipped and a bond breaker was applied, which in this study, it was a sheet of Teflon tape. Following that, the carbon fiber was saturated using the epoxy and the CFRP was applied to the tensile face. Then the anchors were embedded into their anchor holes, the anchor splays were fanned out over the CFRP, and lastly, the shear wraps were applied around the sides of the beams, and a square CFRP patch was placed over the anchors. Now we'll move into the results from the testing, starting with constituent tests. It was found that between the SLC and ACP CFRP coupons, the decrease in tensile modulus as well as the decrease in elongation was statistically insignificant. However, the decrease in tensile strength amounting to 16% was statistically significant. What's interesting to point out, though, about this decrease of 16%, though, is that it's in line with the environmental reduction factor that's suggested by ACI 440.2R for exterior exposure to CFRP, which ACI recommends a reduction factor of 0.85. SOC and ACP dog bones demonstrated different behavior. The SOC dog bones initially demonstrated linear elastic behavior. However, following conditioning, they demonstrated an elastoplastic behavior. In addition to that, tensile modulus also decreased. However, the tensile strength and the elongation of the dog bones increased following conditioning. As for the DSC results for epoxy and putty samples, it was found that after conditioning, the glass transition temperature of the epoxy increased by 35%, whereas for the putty samples, the glass transition temperature increased by 20% following conditioning. And what's being shown here, or what these results are showing, are the competing factors or the competing effects between moisture introduction and heat introduction to the epoxy. So when epoxy is exposed to moisture, it plasticizes, it loses its stiffness, and it softens. However, when it's introduced to heat further cures the epoxy and it promotes polymer cross-linking or in other words, it polymerizes. All right, now moving on to the beam results. So the control unstrengthened beams demonstrated linear elastic behavior up until concrete cracking, and then the specimens failed. When CFRP was applied to the unanchored strengthened beams, again, linear elastic behavior was demonstrated up until concrete cracking. However, following concrete cracking, you see a plateau region here, which is the demonstration of the progression of debonding up until ultimate capacity, and then the specimens failed. Then when anchors are installed, again, you see the same behavior as you did for the past two beams. However, at the region of concrete cracking, rather than the initiation of debonding, you see a change in specimen stiffness, which is the indication of where the anchors engage up until ultimate capacity, and then the specimen fails. Okay, so the orange beams demonstrated here are the load at which concrete cracking initiates for the SLC group. You can see that the anchored bonded beams demonstrate cracking load consistent with the unanchored strengthened beams, whereas the unbonded anchored beams demonstrate a load of concrete cracking consistent with the unstrengthened beam. The reason for this being that the applied flexural strip for the unbonded beam doesn't engage until the anchors do, which is after the fact that concrete has already cracked. The purple bars demonstrate the ultimate capacity of the SLC group. When quarter-inch anchors were used, there's an increase in ultimate capacity relative to the unanchored strengthened beam of 60%, whereas there is an increase in ultimate capacity of 68% and 87% for the 3/8 inch and half-inch anchors, respectively, compared to the unanchored or strengthened beam. The orange hatched bars are now representing the load at which concrete cracking initiates for the ACP group. You can see that there's a slight increase for each beam at which cracking initiates compared to the SLC group. The reason being, as I mentioned earlier, there was an increase in compressive strength of the concrete after conditioning, so that's why this is being observed. And lastly, the purple hatched bars demonstrate the ultimate capacity of the ACP group. And what's important to take away here is that the quarter-inch anchors showed or demonstrated the most susceptibility to the effects of hygrothermal conditioning. The anchored bonded quarter-inch group decreased in ultimate capacity following conditioning, amounting to 24%, whereas the anchored unbonded quarter-inch group decreased by 16% in ultimate capacity. As you could also see, the anchored bonded 3/8 inch group and the anchored bonded half-inch group showed no deterioration following conditioning, and the anchored unbonded 3/8 inch group and the anchored unbonded half-inch group actually improved in capacity, which that's not really well understood at this moment. We're still kind of investigating why that is. And another way at looking at the susceptibility of the quarter-inch anchors following conditioning is by anchor efficiency, which is defined as the ultimate capacity of the anchored beams divided by the ultimate capacity of the SLC unanchored beams. And as you can see from this, the quarter-inch group becomes less efficient in ultimate capacity compared to when it was unconditioned, whereas the 3/8 inch group and the half-inch group remained consistently efficient. In addition to this, the quarter-inch anchors failed primarily by anchor rupture, whereas the 3/8 inch and the half-inch groups failed primarily by strip fracture following ACP. It's thought, or the belief for the anchor rupture of the quarter-inch group is due to the decrease in interlaminar shear strength between the fiber anchor and the composite layer, as well as the insufficient AMR for developing the strip stresses. To conclude, as mentioned, the anchored SLC unbonded beams demonstrated around a lower ultimate capacity amounting to about 30 to 40% compared to their corresponding anchored SLC beams. The quarter-inch anchor group demonstrated the most susceptibility to the effects of hygrothermal conditioning, as there is a decrease in ultimate capacity of 24% for the bonded group and a decrease in ultimate capacity of 16% for the unbonded group. In addition, the anchor efficiency decreased following conditioning. And lastly, the 3/8 inch group and the 1/2 inch group didn't demonstrate any susceptibility to the effects of hygrothermal conditioning. However, they were still able to fail in strip fracture, whereas the 1/4 inch anchors, which did demonstrate susceptibility, failed primarily in anchor rupture. All right, thank you everybody for your time. I can take any questions if you have any.